Okay, this is a revision video based on P9, and today we're going to look at interpreting graphs of motion. So we're going to go through a few things. We're going to go through looking at distance time graphs, which are talking about the rate of change of distance, and from those graphs we'll be calculating speed using the equation speed equals distance divided by time. Then we'll go on to look at velocity time graphs, where we're looking at the rate of change of velocity and calculating acceleration from those graphs using the equation acceleration equals change in velocity divided by time. Higher tier people will also be able to calculate distance from those velocity time graphs, and also we'll talk about graphs where it's important to understand that velocity is a vector. So if we look at this graph first here, you can see here that we've got distance on this axis of the graph, and as soon as you get a graph like this in your physics exam, it's really important that you decide, what am I actually looking at here? We're looking at how distance changes with time. So all straight lines, distance is increasing with time. Distance is increasing with time. At C, notice the distance is not changing, and then at D, the distance is changing, but the slope's going downwards. So at this point here, we're saying we are at the same point as we were here. So this is a journey from home, away from home, and then in D, returning to home. In maths, you'd learn how to calculate the gradient of this line. So the gradient in A is the distance divided by the time. The gradient of this graph is speed, because speed equals distance divided by time. So where the gradient is steeper in B, B represents a bigger speed than A. But both lines are straight, which means that the speed is constant. And C, the straight line that's horizontal, the distance is not changing. We describe the movement as stationary. It's not moving at all. D represents a constant speed returning home. Here's a second distance time graph in a bit more detail, and we've got some numbers here so we can do some calculations. Let's imagine we're asked to find the speed between A and B. So we're looking at the line from A to B. It's straight, so the speed is constant, and we're reading off the values from the graph. At B, this object has travelled 100 meters in 3 seconds. So the speed here is 100 divided by 3, which is going to give us an answer of 33.3 meters per second. We can tell that the speed is faster between B and C because the line is steeper. And if we did have a curve, let's imagine there's a curve on this graph that does this, that's progressively getting steeper and steeper and steeper. Remember what we said, the steeper the line, the greater the speed. So because this line is getting steeper and steeper, the vehicle or object that's moving is getting faster and faster. There's some key facts on the slide here for you to remember. The final calculation, and don't get confused here, would be to calculate the average speed for the whole journey. So imagine if this is you and you set off on your journey and you reach this point here 10 seconds later, you have travelled this far. So 450, the average speed is the total distance, 450 meters, divided by the total amount of time, which is 10. So we can say that for this journey of 450 meters in 10 seconds, the average speed would be 45 meters per second. Average speed, you don't have to actually calculate an average. It just means for the whole journey, because if you look at the line, this vehicle was going slower between A and B and faster between B and C, and then slow down a bit again between C and D. Here's our second type of graph in our velocity time graphs. These graphs will come up more often on the higher tier paper. The gradient of this line here is showing us that the change in velocity divided by time. And that is what acceleration is. So U is the initial velocity. So between A and B, the initial velocity is 0. The final velocity at B is, look at the scale, 15, 16, 17, 18. And the time is 6. So we could say that between A and B, the acceleration is 18 minus 0, or 18, divided by 6, which would be 3 meters per second, or meters per second squared, which is the unit for acceleration. Everybody needs to do that calculation. Again, the steeper the slope, the faster the rate of change, the bigger the acceleration. Notice here, between B and C, the line is horizontal again, but this time look at this axis. What is happening? The velocity is not changing, but it does have a value. So between B and C, there's no acceleration because the velocity isn't changing, but it is traveling at a constant speed. And remember, that means although the acceleration is 0, the forces acting on this object are balanced, and therefore the speed is staying the same. Between C and D, this object is slowing down. It's decelerating. It's decelerating from 18 to 0 in 2, 4, 6, 8 seconds. Finally, on this graph, higher tier people, you need to understand that the area underneath this line is the distance traveled. So if I worked out the total area under the line, your maths teacher would say, work out the area of this trapezium. You would know how many meters this object has traveled. Remember, for a triangle, the distance traveled is half base times height, whereas between B and C, the distance is a rectangle. Let's imagine we were just working out the distance traveled between B and C. We've got a rectangle of height 18 and of base 6. The distance traveled between B and C is the area of that rectangle, and the area, like we said, is 18 for the height times 6, which gives me a total distance of 108 meters. We could do the same for the areas of the triangles and do base times height over 2. Here's 2 graphs from cars showing uniform deceleration in the sloping part of the graph, but also, as you can see here, there's a section of the graph where the cars are continuing to travel at a constant velocity because the graph is horizontal. Car A has travelled at the constant velocity for less time. So if this was a car putting the brakes on, this point here, where the line starts to slope downwards, is where the brakes were applied, and the same here. So car B has travelled further because whoever was driving car B didn't put the brakes on as quickly. And you can see that the slope of the line looks the same. The braking force was uniform, the deceleration is uniform, and the difference in total distance travelled is down to the driver's reaction times, because here this driver was either slower or distracted or tired or had been drinking or taking drugs, and that has caused them to react in more seconds, so slowly, a bigger time to react, and therefore they've continued to travel a bigger distance whilst they're at their peak velocity of 15 meters per second. This graph helps us to understand that we've got a thinking distance, which would be the area under the horizontal part of the line, and a braking distance, which will be the area under the triangle of the sloping part of the line. Final type of graph here, we've got a velocity time graph here that's got both positive and negative numbers, and that's because velocity is a vector. Remember, a vector means a quantity which has both magnitude and direction. So here, this is a journey in a straight line traveling in one direction, a positive velocity, let's say to the right, constant velocity to the right, uniform deceleration, and then at this point here, the velocity goes negative. That means that the object is traveling in the opposite direction. So a negative velocity, I'm accelerating to the left. My velocity is increasing to the left, and then a constant velocity to the left. All of the calculations we've talked about here would be the same. The slope of the line is the acceleration. The area underneath the line is the total distance traveled. All right, the key bit of understanding in this graph is that all of this part of the graph above the line where they're positive is to the right, and all of this bit of the graph below the line is to the left. So we tend to call in calculations in physics, where we've got vectors like velocity and force, a positive velocity to the right, a negative velocity to the left, okay? Because it is a vector quantity.